The new V6 diesel engine generation, OM642, was introduced in 2005 and has gradually replaced the previous OM612, OM647 and 648 engines in passenger cars and vans. The table shows the main specifications of the engine when installed with a 7-gear automatic transmission. The 629 V8 diesel engine was introduced in the autumn of 2005 as a replacement for the 628 engine. The table shows the engine specifications with a 7-gear automatic transmission. The overview shows the previous generations of CDI engines at Mercedes-Benz. The introduction of the 642 and 629 engines launched a new generation of common rail diesel direct injection systems. Depending on the vehicle it is installed in, it is called the CDI-4 in the E320, the CDI-5 in the 221 series S-Class, and the CDI-6 in the 204 series C-Class. The low-pressure system supplies the injection system with sufficient fuel and pressure in all situations. The diagram shows a simplified version of the fuel circuit of the OM642. The high-pressure system is faded and the low-pressure system is bold. The layout and function are largely identical to the CDI-3 system. You are already familiar with this from the third part of the program on common rail direct injection. Click on the CDI systems to compare them. Move the mouse over the highlighted components to see what they're called. Click on the components for a brief summary of what they do in the system. The swirl pot is the housing of the fuel delivery module and prevents the fuel pump from drawing in air when the fuel is low or when cornering. The fuel pump delivers the diesel fuel to the supply line of the low-pressure system. If a line is blocked, the pressure relief valve restricts the pressure to a maximum of 8.5 bar. The fuel tank contains the fuel and is equipped with 4 suction jet pumps, which draw up the fuel to fill the swirl pot. The leak oil line takes away excess fuel from the injectors. The main fuel filter removes impurities from the fuel by catching them in the filter material. The fuel supply line provides the high-pressure pump with the right amount of fuel. The fuel return line delivers the excess fuel from the pressure control valve on the rail and the fuel pressure relief valve to the fuel tank. The fuel pressure relief valve maintains a pressure of around 4 bar in the low-pressure circuit. The fuel temperature sensor registers the temperature of the fuel and reports it to the CDI control unit. The flow control valve is activated as required by the control unit and regulates the fuel flow to the pump elements of the high-pressure pump. The flow control valve is activated as required by the control unit and regulates the fuel flow to the pump elements of the high-pressure pump. The fuel temperature sensor registers the temperature of the fuel and reports it to the CDI control unit. The fuel pressure relief valve maintains a pressure of around 4 bar in the low-pressure circuit. The fuel supply line provides the high-pressure pump with the right amount of fuel. The fuel return line delivers the excess fuel from the pressure control valve on the rail and the fuel pressure relief valve to the fuel tank. The leak oil line takes away excess fuel from the injectors. The fuel tank contains the fuel and is equipped with 4 suction jet pumps, which draw up the fuel to fill the swirl pot. The fuel pump delivers the diesel fuel to the supply line of the low-pressure system. If a line is blocked, the pressure relief valve restricts the pressure to a maximum of 8.5 bar. The swirl pot is the housing of the fuel delivery module and prevents the fuel pump from drawing in air when the fuel is low or when cornering. Maybe you have already noticed the difference between the two low-pressure systems. Compare the two systems once again and then click on the components in the low-pressure system of the 642 engine that you think have changed. On the engines from the CDI-4 onwards, the leak oil line of the injectors leads to the fuel supply line in front of the main fuel filter, rather than to the return line as on the CDI-3. The reasons for this modification are detailed in Chapter 4. What is the correct label for the low-pressure circuit on the 642 engine? Drag the component names to the right positions and then click on OK. Very good. You have named all the components correctly. The high-pressure system controls and maintains the necessary fuel pressure for injection. The illustration shows the fuel circuit on the OM642 as an example. The high-pressure system is bold and the low-pressure system is faded. The layout and function are largely the same as those of the CDI-3 system, which you are already familiar with from the third part of the program. Click on the CDI system to compare them. Move the mouse over the highlighted components to see what they are called. Click on the components for a brief summary of what they do in the system. The fuel injectors inject the pressurized fuel into the cylinders. The high-pressure pump delivers the fuel from the low-pressure circuit and compresses it to the required injection pressure. The pressure relief valve controls the fuel pressure in the rail. It is operated by the CDI control unit using a PWM signal. The rail stores the required amount of the fuel with the necessary pressure for injection. The rail pressure sensor records the current fuel pressure in the rail and sends an electrical signal to the CDI control unit. The rail pressure sensor records the current fuel pressure in the rail and sends an electrical signal to the CDI control unit. The rail stores the required amount of the fuel with the necessary pressure for injection. The pressure relief valve controls the fuel pressure in the rail. It is operated by the CDI control unit using a PWM signal. The high-pressure pump delivers the fuel from the low-pressure circuit and compresses it to the required injection pressure. The fuel injectors inject the pressurized fuel into the cylinders. Apart from the modified course of the leak oil line, there is another important difference between the CDI-3 engine and the new ones. Compare the two systems once again and then click on the component of the 642 engine that you think has changed. The design and layout of the fuel injectors in the engines from CDI-4 onwards are significantly different from those of older systems. The new injectors are based on piezoelectronic technology. The new injectors are described in detail in Chapter 5. Which of the following components are part of the high-pressure circuit on the OM642? Click on all the right answers and then on OK to confirm. That's right. The high-pressure circuit consists of the high-pressure pump, the fuel injectors, the rail and the rail pressure sensor. You are already familiar with the high-pressure control system of the CDI-3 with the pressure and flow control valve from the third part of the program series on common rail direct injection. The following table provides an overview of the conditions for high-pressure regulation on the 642 and 629 engines. Click on the valves in the table to find out more. In the first 30 seconds after the engine is started and at fuel temperatures below 20 degrees Celsius, the high pressure is always regulated by the pressure control valve. Also, when idling at fuel temperatures below 70 degrees Celsius and in overrun mode, the fuel high pressure is controlled exclusively via the pressure control valve. 30 seconds after the engine is started, or when the fuel temperature reaches over 20 degrees Celsius, the high pressure is exclusively controlled by the flow control valve. This also applies when idling at fuel temperatures above 70 degrees Celsius, at engine speeds above 1200 rpm, and at injection quantities above 15 cubic millimeters per stroke. On the OM629, the high pressure is only regulated by the pressure control valve for the first 5 seconds after the engine is started, or until the fuel reaches a temperature of 20 degrees Celsius. At fuel temperatures above 20 degrees, the flow control valve takes over high pressure control 5 seconds at the latest after the engine is started. During normal driving at large injection quantities and high engine speeds, the high pressure is regulated exclusively via the flow control valve. On the OM629, the fuel pressure can be regulated exclusively by the pressure or the flow control valve, or by both combined. This dual actuator mode is called coupled pressure control, or CPC for short. The diagram shows the ranges for the 3 high-pressure regulation modes on the OM629 according to the speed and the injection quantity. What do you think? Which range is coupled pressure control used in? Click on the corresponding area on the diagram. Correct. The rail pressure is controlled using both valves when the engine is idling, in overrun mode, and with small injection quantities at speeds up to approximately 2000 rpm. Both valves are opened and control the rail pressure together. Coupled control avoids sudden switching, which would cause pressure fluctuations and noise with the larger fuel volume of the V8 engine. CPC therefore improves comfort because the transition between the 2 control modes is gradual. How is the rail pressure controlled on the 642 and 629 engines at normal fuel temperature? Click on the correct valves for each situation and then on OK to confirm. Very good. When the engine is started, the rail pressure is controlled on both engines by the pressure control valve until the fuel temperature reaches 20 degrees Celsius. During normal load situations, the pressure control valve on both engines is closed, and the rail pressure is controlled solely by the flow control valve. When idling, the rail pressure on the OM642 is controlled exclusively by the pressure control valve. On the OM629, the rail pressure is controlled by both valves in this case. On the CDI-3, there is no fuel cooling. When various operating conditions occur simultaneously, the fuel may therefore overheat. What do you think are the conditions for this? Click on the right answers and then on OK to confirm. Very good, that's right. At high outside temperatures, the fuel is warm to start with. At high loads, it is heated even further. If the fuel level is low as well, which means only a small quantity of fuel is in the circuit, critical fuel temperatures may be reached. To protect the tank from overheating, the CDI control unit evaluates the signals from the fuel temperature sensor. If the temperature rises to more than 90 degrees Celsius, the CDI control unit uses the flow control valve to restrict the fuel supply to the high-pressure pump. The engine power is markedly reduced. If this happens, the customer may complain, as he may not know why the engine power was reduced in these circumstances. Also note that there will be no error message in the control unit, since this is a normal system protection function. One important new feature of the common rail direct injection system of the 642 and 629 engines is the use of piezo injectors. These make use of the special properties of piezoelectric crystals, or ceramics, that expand slightly when a high electric voltage is applied. The piezo injectors therefore contain several hundred piezo elements connected in series in order to effect a sufficient change in length. Find out about the design of the injector by moving the mouse over the illustration. Click on the components for more information. The socket is for the electrical connection of the injector and is connected to the CDI control unit. The high-pressure port of the injector is connected to the rail via short high-pressure lines and supplies the injector with fuel at rail pressure. Excess fuel flows out through the leak oil line. The piezo elements are contained in the actuator module. This is directly connected to the electrical connection of the injector. Because of the very slight expansion of the piezo elements in the actuator module, the coupler module is required. This acts as a hydraulic converter and amplifies the movement of the actuator module. Its other task is to compensate for the play between the individual parts at different temperatures. The valve set consists of several pressure chambers connected via throttle valves. The high-pressure line is also connected here. The nozzle module contains the needle, which opens towards the inside during injection. Watch how the piezo injector works. The enlarged section shows a simplified model of the valve set and the nozzle module in the de-energized state. The rail pressure acts in the control chamber and keeps the needle closed. No injection takes place. Click on the CDI control unit to start injection. When the high voltage is applied to the actuator module, it expands and the valve pin closes the bypass hole. At the same time, it opens the connection to the leak oil line. The drain valve opens and the pressure in the control chamber is reduced. The excess fuel is minimal compared to solenoid valve injectors. It flows past the valve pin into the leak oil line. The lower pressure in the control chamber causes the nozzle needle to open and injection begins. Click on the CDI control unit again to finish injection. Injection is finished by de-energizing the actuator module, causing it to contract. The valve pin releases the bypass and also closes the leak oil line. The outlet throttle, inlet throttle and bypass increase the pressure in the control chamber back up to the rail pressure level. The increased pressure in the control chamber causes the nozzle needle to close and injection ends. If you want to repeat the process, click on the CDI control unit. What are the main components of a piezo injector? Drag the component names to the right positions and then click OK. Well done, you got it right first time. What conditions of the piezo injector do these diagrams show? Click on the right answers and then on OK to confirm. Very good, you found the correct conditions. From the CDI4 onwards, the leak oil line runs to the supply line of the main fuel filter. This is an important difference to the previous CDI systems. The leak oil line has two functions, depending on the engine situation. Try it out. Click on the Ignition On button and watch what happens. When the ignition is switched on, the fuel pump is activated. It pumps fuel into the supply line. The fuel pressure relief valve maintains a pressure of around 4 bar in the low-pressure circuit. The supply pressure thus acts on the piezo injectors and fills the coupler module in the injector. What happens when the engine is running? Click on the button. When the engine is running, the high-pressure pump generates the necessary rail pressure. Excess fuel flows through the pressure control valve and the fuel pressure relief valve on the high-pressure pump to the return line and the fuel tank. In the leak oil line, a throttle in front of the T-junction maintains a pressure between 5 and 10 bar, depending on the engine load. This is necessary so that the coupler module in the piezo injector works correctly. Behind the T-junction, the 4 bar supply pressure generated by the fuel pump applies. Piezo injectors have a number of advantages compared to solenoid valve injectors. Piezo electronically controlled injectors are not only smaller and lighter, they can also be switched faster. This permits flexible multiple injection with very small, precisely metered quantities of fuel. This leads to reduced pollutants from combustion and new options for exhaust gas treatment. 1 or 2 pre-injections in the compression stroke prevent the emission of blue and white smoke after a cold start and reduce combustion noise. If necessary, up to 2 post-injections can be used at the end of the power stroke to regenerate the diesel particulate filter. The manufacturing process for the injectors means they vary within a defined tolerance range. Therefore, all the injectors are measured and individually coded after production. Click on the injector to find out more. From the CDI-4 onwards, the code has 7 digits, because it takes into account the electrical properties of the injector as well as the mechanical ones. The correction of the mechanical properties of the injector is known as the injector mixture compensation. The correction of the electrical properties of the actuator module is known as the injector voltage adjustment, and is based on the change in length with which the actuator module reacts to the control voltage. Together, they determine how rich or lean the injected fuel mixture is in different situations. When an injector, or the CDI control unit, is replaced, the codes of the injectors have to be entered in the control unit. If this is not done, or if the codes are incorrectly entered, the injectors are not properly activated, and the following problems may arise: smoke, rough running, or loss of power. Due to aging, the mechanical and electrical characteristics of the injectors change over time. To compensate for these changes to the injectors, the CDI control unit is programmed with what is known as drift compensation. This software function includes zero quantity calibration and quantity mean value adaptation. These two functions are described on the next pages. During the service life of an injector, friction, when the needle opens and closes, causes wear on the nozzle module over time. To compensate for this, older injectors have to be activated slightly longer to inject the same quantity of fuel as new ones. To determine the necessary activation time, the CDI control unit first sets a constant rail pressure for overrun mode. The activation time for a single injector is then increased until injection takes place. Try it out by clicking the crankshaft diagram. After a certain activation time, the needle opens and a small quantity of fuel is injected. The control unit detects a slight increase in speed via the crankshaft Hall sensor. This is not perceptible to the driver and is clearly linked to the injected fuel quantity, which is known as the zero quantity. The activation time, thus calculated, is used by the control unit as a correction value for calculating the injection time. The process is repeated for all injectors in succession. These calibration values are stored in the engine control unit. The quantity mean value adaptation is an adaptation of the quantity of recirculated exhaust gas and the injection quantity to compensate for gradual changes to engine units. During load operation, the CDI control unit calculates the intake air quantity from the signal of the hot film air mass sensor. The mixture is recorded using the oxygen concentration in the exhaust gas measured by the lambda probe. If the values are not correct, the exhaust recirculation rate and the injection quantity are adjusted so that the differences do not affect the exhaust emissions. Also, the following components affect the mixture: hot film air mass sensor, broadband lambda probe, rail pressure sensor, and air filter insert. This means that the quantity mean value adaptation must be reset when these components are replaced. What are the names of the functions described below? Drag the names to the right place in the table, then press OK. Very good. The injector quantity compensation, or IMER code, compensates for the mechanical variations of an injector that arise during manufacturing. Gradual changes to the engine units are compensated for by the quantity mean value adaptation. The exhaust recirculation rate and the injection quantity are adapted to the set values. Zero quantity calibration adjusts the activation time of the injector for wear to the nozzle module. Electrical tolerances in the expansion of the actuator module are recorded at the factory using the ISER code. When certain components are replaced, the parameters have to be changed in the CDI control unit. Which parts are they? Click on all the right components and then on OK to confirm. Very good. The injector code has to be re-entered when one or more injectors are replaced. If the CDI control unit is replaced, the codes of each injector must be entered again. When the rail pressure sensor, the hot film air mass sensor, the broadband lambda probe, or the air filter insert is replaced, the quantity mean value adaptation must be reset in the CDI control unit.